Hello, welcome. This is now a NXL FP1 video. This is on the last section of the numerical solutions to solving equations. This particular one looks at something called the Raphson process. Now, just two people who came up with this idea, really. It's not physics, so they need to give you a whole lecture on how they came up with the law, this, that and the other. So as I said, I'll just give you, this is actually personally what I think to be the easiest FP1 topic if you're doing it so far, in terms of you've just done complex numbers, and this is your final video on numerical solutions, and this is by far and away the easiest topic so far, definitely the easiest method. And when I've looked through the past papers, this seems to be quite a common question they ask you. Obviously they ask you the others as well, but I've seen this method asked more than the others. As I said, correct me if I'm wrong, but that's what I've seen through going through the FP1 NXL papers. Maybe different for other exam boards for obvious reasons. But as I said, it's very easy. So it's just a case of using this formula. So it's x to the subscript of n plus 1 equals x subscript n, take f of xn over f dash of xn. Now what does that all mean? Well, when you make sense of it, it's just a case of inputting the numbers, obviously. So this should look, obviously depending on where you are with your A-level maths, but this should look like an irritation formula, which I think you do, it's lost track of what you do, but you do it in one of the cores. I think it's either core 2 or core 3 you start using. I'm pretty sure it's core 2. Okay, so what does this all mean? Okay, well, this xn is the business that we want to focus on, really, to start off with. This xn is just, because obviously it appears in all different parts of the equation, this xn just means the first approximation. So we'll just label it as first approximation. I just put first approx, shorthand for first approximation. Okay, so therefore this is the second approximation, and x is subscript of n plus 1. Okay, now that does not mean whatever xn is, add 1 to it, it's just the next approximation, so it's the second approximation. But obviously if you've done irritation, you knew that already, the second approximation. Now, therefore these two is just a polynomial kind of thing. Okay, so this is just the f of the approximation, which is just subbing in this number into the equation. So whatever this approximation is, subbing it in for the value of x and working out an answer. Obviously that will become more apparent as we go through equations. And then this bottom bit is just the differential of the equation, and then we sub in what the first approximation is. Okay, so it's the derivative, and then we sub in the approximation. Can't really do much more than that. As I said, it's quite helpful to go through an example to this. But just before I do, you may be saying, okay, well, yeah, say we know all this, yeah, apart from obviously the second approximation, the next one, and the next one, because obviously we'd have to work that out. But how does this help us in order to get an approximation? Because obviously it's numerical solutions to equations, so it's obviously going to be helping us to find the root of the equation. Now, the one we've used before is that x cubed plus 2x take 2 is equal to 0. And that is equal to f of x, okay? And that's the equation we use. How does this help us to solve that when we've given roots, okay? Well, what we do is we just pick an approximation. Now, this one we know has a root between 0 and 1, okay? We know that. We've proved that in the previous two videos. I think it's 0.8, but say we didn't know that. Obviously, we know it's something to 0.8. This rule, what we do is we just put any number between 0 and 1, because obviously then it will continue using this formula to get us to the approximation. And the reason why we can use any number is because this process just keeps narrowing it down, and we'll either keep increasing it to the root or keep decreasing it to the root. So obviously we know the root is 0.8, but to one decimal place. But say we put 0.2, say, well, how can we get to 0.8? Well, obviously then you just sub it in and you will keep getting to that. It'll become obvious. So it doesn't matter what one you pick. Now personally I would pick because you've got a takeaway, it makes sense to pick the biggest root. So I'd pick 1, and then it would work down from that. So obviously it's not one for every equation, but personally I would pick the biggest root. Sorry, not the biggest root, the sort of the most extreme, one of the two extremes of, you know, where it says the root lies between 0 and 1, I would pick the largest figure it gives you, so obviously 1 in that case, or you know, you can follow the logic. Okay, so then it's just a case of working this all out. But just like we did with when we do iterations, instead of doing what we're going to do now, where we just do, okay, well we'll just simply follow the formula and put in whatever we know. Okay, so the next approximation x2, because we say, okay, well sometimes they call it, I'm going to call it x1, sometimes they call it x subscript 0, just the first value, doesn't matter. I'm going to choose that to be 1. Now, as I said, you can choose that to be any value that lies between 0 and 1, but it doesn't really matter. Okay, so I pick 1, so therefore x2, this is equal to the first approximation, which we said is 1. So it's 1 take f of 1 over f dash of 1. Oh, sorry. Okay, so then it's just a case of subbing in these actual numbers. So that's really what the raw thing would look like in contrast to this. Then we're just going to work out what f1 is and f dash of 1. Now, to work out f dash of 1, so this is derivative, and then we sub in 1, we need to work out the derivative of this function, which obviously, when we work out the derivative, first derivative, we just do f dash of x, and that gets us 3x squared plus 2. Okay? So you just do the f of f dash of 1, so you sub in 1 where it's 3x squared plus 2. Okay? So it's 3 times 1 squared plus 2, so that's obviously just 3 plus 2, so that's 5, okay? And then f of 1, well, you should know that, well it's 1 cubed plus 2 times 1, take 2, so that obviously gives you 1, okay? So therefore f of 1 is just 1, okay? So therefore x2 is equal to 1 take 1 over 5, or 1 take 1/5. Now we should know straight away that's 4/5, so therefore x2 is 0.8. And you go, oh, that's what we already know. But maybe it doesn't want it to 2 decimal places. You will keep going until it rounds to whatever number you want to. Okay. So instead of doing this method and following in this vein of doing, you know, f of 1. So on the top we did 1 cubed plus 2 times 1 take 2. Sorry. And we did that over the f dash of 1, which was 3 times 1 squared plus 2. Instead of putting in your value here, you know, like it is asking you to, you can just, as we do with iterations, we just use the answer button, okay? Because obviously the calculator has a memory, so just whatever approximation you put in this case, our first approximation was 1, you clear your calculator's memory and set your calculator's memory the answer to be 1. So, I mean, as it's obvious, but for the benefit of those that don't know, I'll just demonstrate. So it's only going to take a second. So okay, so you clear your memory for your calculator. You should obviously know how to do that. And then you press 1, press equals, and then when you press answer, that is now stored as your answer. So obviously, then what you'd do is you'd follow the formula that we've got up here. Sorry, my hand's a bit in the way there. So we said x1, which is the first is the first approximation. So there you put 1 is, because 1 is your first approximation. However, because we want to just keep pressing answer, we're just going to hit the answer button. And then we want to follow the formula, so it's f of x, n, so first f of the first approximation. So you take away, and then obviously you just split it up. Sorry, I'm just trying to do it from the calculator here. Okay, so you split it up, and you do it just f of 1. So instead of putting 1 cubed, just put answer cubed, because obviously this formula is going to be the same. We're not changing the formula, but just subbing in the new answer. Okay, plus, plus 2 times the answer. Take 2, and then you do the same on the bottom, sort of thing. Same principle. So it's because it's 3 squared, it's 3 times the answer, and obviously you can bracket that off as I'm doing, and then you add on the 2. Okay, so it's just really a case of putting it into a calculator like I have done there, because it matches the formula that we've worked out. Now obviously for any of this you have to work out f dash of x and f of x, so you can sub them all in. Okay, and then you just hit answer. Now as said, I proved you get 0.8, but that's what we worked it out to be when we did the bisection method. But if we want it to do a bit more accurately, we keep hitting the equals button, and you can see the answer continues to change. But oh, hang on a second, look, it doesn't seem to be. I mean, these numbers at the end are changing, but these two, it depends what degree of accuracy you want it to. Now, in this instance, particular question in the exam, it's asked us to 2 decimal places. So even if we kept pressing equals for the rest of our lives, and I'm pretty sure, if you wanted to waste your life, that's one way of doing it. These wouldn't have changed. So no matter how far you go, it's only these numbers that would change, and you will get to a certain point, and obviously it'll be x8 or whatever, and they won't change. But really, what we're looking at here is the first few significant figures not changing. Okay, so really, even though we've said the root of that is 0.8, really when we're doing it accurately it's 0.77, which obviously rounds up to 0.8, which is what we got in the second approximation, which is why you can kind of see it's just how accurate do you want it. Now, as I said, you wouldn't have necessarily known that was the root, but I just picked the equation that we've been using for the previous two methods to enable us to work it out. Okay, now what I'm going to do now, so that's really the end of the Newton-Raphson process. There's nothing more that we can add to that. I mean, it just applies to whatever particular question comes up in the exam, and obviously I'll be working through a few examples as we go on. But that was really, as I said, for this one, because it's so easy to understand, I don't need to go through any more examples, I don't think. I mean, you're more than welcome to send me any examples you want to, and I will try and produce a few videos before the exam. But really, that's as hard as it gets, and that's, you can see, not very hard at all. But obviously FP1 gets a little bit more difficult than that as we go on. Okay, but what I'm going to do now, so for the benefit of those that were just interested in the Newton-Raphson process, the video is now over. But what I'm going to do now is obviously add a few more minutes to the video, as I'm going to talk a little bit about I'm going to talk you through. It's just recapping a bit of information that you already know. So I'm just going to sort of highlight in a few, I'm just going to do one board full of the 3 methods that you can use to solve equations. Now obviously you get factorising, etc. I'm not going to include them because we're in FP1 and you're a bit more intelligent than that. Okay, so really what I'm just going to be doing is covering the first method, which was the bisection method, then the linear interpolation, and then obviously the method we've just done. But I don't need to, as I said, I'll just be writing a bit on the board, such as I'll be writing a formula on there, and then going over a quick recap of how we calculate them. Okay, so as I said, if you're not interested in that, you can switch off. Right, so the first method that we looked at for calculating the root of an equation was the bisection method. And what we said, I gave in that video that I did, I gave a little bit of an overview, and I said, okay, well, the first thing to do when you're told an equation has a range, so an equation might have a range between 0 and 1, okay, then what you would do is you'd sub in, so you've got an equation f of x. Now the equation I used was x cubed plus 2x take 2, which is the equation I've just used before, and obviously you make it equal to 0, but I'm assuming that is already equal to 0. Okay, and then you work out what f of 0 is, work out what f of 1 is, and half the range. So obviously halfway between that is 0.5, okay? But if you weren't sure, you just add the two extremes together and half it. So you would add 0 and 1 together and half it. But as I said, that's for, if you weren't sure of a range and it was a little bit more complex. Alright, but that's basic. Then you would work out where is the change of sign. Is the change of sign between 0 and 0.5, or is it the change of sign between 0.5 and 1? Okay? If, obviously, as we know, it's 0.8, so it's not going to be between 0.5 and 0 and 0.5. So we assume the sign of when you put in f of 0 and f of 0.5, the sign stays the same. And as we assume this kind of curve is not going to be doing all this business, okay? It's not going to be weirdly changing direction of course of the natural progression of the graph. So it's not going to be doing any weird skews. So therefore we can assume all of this is going to have the same sign. Now you can go through really anally if you want and do f of 0.001, f of 0.002 and go on and on. But you will find there's not a change of sign between 0 and 0.5. So therefore it must be between 0.5 and 1. And you keep halving the range until you can categorise a range which has a change of sign in it. And I think that's like between 0.8125 and whatever it might be. Okay, so when you've got a range that has a change of sign, then you just round it to whatever degree of accuracy you want. So in this case we rounded it to 0.8. Okay, so that's just a brief overview. If you want some more info on that, please do check out my other video. But as I said, I'm assuming you've already learned that, and it's just a bit of a recap of the method. Okay, so the next method that we looked at was all about the linear interpolation method, and that was just a fancy word when we used when we compared the shapes. Now this one is probably the most complicated method of the three, and that's not because it's in any way difficult to understand. It's just it's easy to make some mistakes going through it. Okay, so what you would do is obviously so we pick this equation again. As I said, it's just comparing the methods. And we're told the range is between 0 and 1. As before, you would work out what f of 0 is and f of 1 is, but not necessarily looking at the change of sign, okay? So, let's just draw a basic sort of graph, okay? So we've got y and x. Now, I'm not going to draw a full 4 quadrants because we know it's between 0 and 1, so I'm not going to bother doing all the minus numbers, okay? And then what you do is you draw 2 points on it, so you draw what f of 0 is, and obviously the x value be 0. You work out what y is, because when you find out what f of 0 is, what you're doing is, well, what's y when x is 0? Okay, you get a value for that, well, whatever that might be, and then you do what f of 1 is. So when x is 1, what's y? And then you draw, assuming that the graph goes straight, this constant gradient, which obviously it isn't, but as I said, this is an approximation. Okay, so then what you would do is you would call this approximation where it goes through the x-axis to be alpha. Okay, now as I said, you compare similar shapes. So the two shapes that we can see on there is these two triangles. Now the method I used was okay, well let's call this triangle A and this triangle B. Now as I said, you have to do that. It's not actually part of the method. But it's the method that I use, and the reason we can do that, so the reason we can compare them to be similar shapes is, well, obviously similar shapes, the main similarity is that they have the same angles, and we can assume that because, well, obviously they both got a right angle, and because of parallel angles or whatever they are, these two angles will obviously be the same, okay, so therefore these two must be as well. Alright, so what we would do is we would find this alpha, and the way we would do that is by using a method to compare similar shapes, okay, to work out the length of this, because the length from the start of A to alpha is obviously what alpha is, because obviously this is 0, so whatever the length is what alpha is. Okay, so what we did was we did the height of B over the height of A. Sorry, height of B over the height of A. And by the height of A, it's actually the length downwards. But obviously you need to make this length positive because you can't have a negative length. So that's the height of A equals the length of B, which is obviously from alpha to 1. So it's 1 take alpha if you were putting the length in. Okay, so it's the length of B over the length of A. Now, obviously you can have this as, the length of B over the length of A equals the height of B over the height of A. Doesn't matter which way you do it, or if you want to flip the fraction, as I said, you might want to do the height of the triangle A on the top. It doesn't matter, you will end up with the same answer, okay? But that's just one example. It's really just comparing. It's just comparing the ratio of the heights and the ratio of the lengths, which should be the same if they're similar triangles, which obviously they are. Okay. And then what you would do, obviously, because we've got this one take alpha and alpha business on the bottom, you would work out whatever alpha was. As I said, that was an approximation, and I think the first approximation of this, if I remember, was 2/3, which we obviously know is 0.6 recurring. Okay, and then what you would do is, okay, well, this is an approximation, and we assume at 0.666 or 2/3, we assume that to be where it crosses. Okay, so therefore, ideally, if this method is right, now very rarely you would get the first assumption or approximation to be the actual value where it crosses. Okay. Then obviously you would put f of alpha, or in this case f of 2/3, the same thing, equal to a value. Now I think it can out to be a negative value. Okay, so obviously this isn't where it crosses. At this point of x is 2/3, we know it's still below. So therefore what we do is we redraw this. We say, now this must be wrong, because obviously this graph that we've preliminary drawn, the first attempt, the first draft of drawing this graph of what the intercept could look like, it's obviously wrong, because we know from putting the value of alpha in to be 2/3, we know this intercept is not 2/3. So what do we do? Well, you redraw this method, redraw another graph. But instead of drawing it from where x is 0, because we know by that method, if we were to redraw that, we just end up with the same thing, and we end up working out the same value for alpha. So we have to modify this graph, we have to redraw the new intercept. Now we know that when x is 2/3, we get this negative value. So we draw x to be 2/3 on, and we pick whatever point it is. Now it doesn't have to be accurately drawn, as I said. I'm not sure exactly what it is. And whatever point that might be for y, you would draw it up. Now you still know when x is 1, y is 1. Yeah, whatever x is. Okay. So therefore we end up with two new triangles. Okay. And this new value for alpha, which we call alpha subscript 2, or the second approximation. Okay. Now just as we compared the two similar triangles before, we do the same thing again. We just repeat this method until we sub in a value for alpha, where we get an f value. So when we find this approximation for alpha and we sub it into the equation, which is that one over there, and we get a change of sign, we know that alpha is the approximation and it's the first. So the first change of sign occurs from this alpha is what we assume to be the x-intercept from the graph. Okay. And as I said, that's all that really the method goes on to say. And the final one that we've just done today is we said, okay, well this we just use a formula, the x subscript n plus 1 is equal to xn, take the f of xn over f dash of xn. As I said, we've just gone over that today, so that should be fairly fresh in your mind, but just to recap it anyway, it's just a case of using your knowledge of irritation formulas, which I've got one on my nose at the moment. Not the formula, just in irritation. Although there is one in a room with a dog there called my brother, which that's an irritation too, but they're different things, unfortunately. Okay, so, right, anyway, as I said, this method is just using the irritation method, so it's the next approximation is equal to the first approximation. Take the take the value of the equation when we sub in the x to be the first approximation over the value of the differential equation. So when we differentiate that and we sub our first approximation in there, and that will equal our second approximation, and you keep following the formula until you get whatever degree of accuracy you'd want, and you could prove to yourself that is the case. Okay, by subbing it in, and you should see a change of sign. Okay. Now, sometimes that equation doesn't always converge to give you an answer, but in the questions they will ask you, obviously it should, unless you've done something wrong, unless the examiner just wants to pee everyone off on the day, which is understandable. You know, if it's the last day on the job, it's just like, this is my last exam, I'm going to screw it up for everyone. But hopefully we don't get that kind of examiner, the person who creates the exam, anyway. So really, it's just a case of using that formula. Okay, so as you can see, I think that's definitely the easiest method, and I would always choose that method if you could. But as I said, it doesn't always work for every question. Alright, so hopefully you can see why it's nice and simple. Now, really, this equation is sort of like, think I did it in C3 actually. Yeah, when we did the irritation, if you go into, when you're going to do C3, if you've not done it already, towards the end you get something vaguely like this, where you have to work out an irritation kind of thing. And if you want to check out the reasoning behind this, as I said, I don't really want to go through because it's already on a C3 video. So if you go to my C3 playlist and you look for, let's do it live now. So let me just get it up for you. As I said, it doesn't really matter. Let me just, as I said, you can switch off now. I'm just trying to find what the video is called. So if you're interested, obviously you'll stick on. Okay, so if you go on my C3 playlist, so it should be an XL C3. Just find it a second. So I haven't uploaded it to this playlist for a while, so it's not sprouting on me straight away. Oh god, it's not. Definitely put one up there. Oh god, it's like I'm missing a playlist off. I do apologise. There should be a C3 video playlist on there. I'm probably passing over it because I'm going way too fast. I'm sure I am. I'm sure it's nothing. There's a playlist on there for C3 and there's an irritation video on there. So if you look through the irritation playlist, which is only C3 one, you should find something vaguely like that. Sorry it's not been particularly helpful. I'll probably do another video explaining where it is. But I'm just waffling. Anyway, thanks for watching and we'll see you in the next video.